This video is an overview of the third midterm, considering that we had both short answer and open response. The point distributions are given here, and once again, the total points on the exam were 134. I scored it as a percentage out of 130, so that was, in a sense, sort of dropping one of the short answer questions, with the class average being in the low 80s. In this video, I'm going to talk about features of the open response. First question to choose from involved ideas with liquid crystals. The first prompt was considering a liquid crystal and discussing its viscosity. So the very best answers within this would be communicating an understanding of the liquid crystal phase, how was it structured, and then describing what would contribute to a high or low viscosity. Consideration of how viscosity could be an anisotropic property, that was a great bridge between the two of these. I bring that up quite often. Folks went to the same analogy that I introduced in class, thinking about uncooked spaghetti. And what did it mean to have uncooked spaghetti display a certain ordering when it was in the box? But if you open it up, what did it mean to have that quite readily flow out? And what that would mean, having it quite readily flow out in one direction, but perhaps not in a different direction. Some really nice discussions then of how the liquid crystal phase, amongst its properties that were anisotropic, would be viscosity. Next one, this was considering how some molecules that adopt liquid crystal phases have similar structural features. The features that they have, thinking about rigid molecules with polar groups that can exhibit relatively strong attractions and cause the liquid crystal molecules then to adopt a particular ordering, a particular alignment. This is the discussion I was looking for. Second one here, we have two questions involving the electronic structure of solids. First one was considering the sieve electron model and its ability to explain how a light-emitting diode operates. The best responses within this communicated how LEDs function based on the MO description, that's a band structure description, and then contrasted this with the sieve electron model and pointed out how the sieve electron model was really giving us no insight into the excited states that we would have possible, differences in electronic energy levels. So in order to explain a light-emitting diode, we needed that band description. The second one was looking at some conductivity data. This was a very effective question to have people share their understanding. So if we look first of all at the undoped germanium, if we think about semiconductors, remember the column on the periodic table, silicon, germanium, tin, that has 4 valence electrons. And that's where we sort of start when we're thinking about a semiconductor. If we're adding electrons and we have 4 valence electrons for that particular column, we find that we're populating then the valence band, and there's a band gap between the valence band and the conduction band. That's shown here over on the left-hand side for an undoped semiconductor. That would be, in the data here, the undoped germanium. We find that it has very low conductivity because the gap's all filled up. As the temperature rises, we're able to promote electrons to the conduction band, and that's why the conductivity increases. A lot of really strong answers within the first aspect of the analysis there. If we're thinking about the germanium doped with gallium, we've now doped in an element to the left of germanium on the periodic table, so we have fewer valence electrons. If we have fewer valence electrons, we're making a p-type semiconductor. So now we've made a hole that we would have with ability for the electrons to move down here in our valence band. So in this case, it begins with a very high conductivity. In some ways, it's behaving like a metal. And if we think about metals, as the temperature raises, it turns out the resistance increases, their conductivity goes down, because now we have particle motion of the different atoms themselves. In a way, they can get in and disrupt the path of the electrons that would be moving through. And so that particular scattering, that then diminishes the conductivity, and that would be this final feature right here. When students within their response described this in terms of the increased kinetic energy, that's what I was reading it for. A lot of really strong answers overall within this topic, and this is an important topic, not these particular questions, but the electronic structure and how molecular orbital theory is used to describe the electronic structure of solids. Important idea as we think for the final exam. Couple questions here involving enthalpy in different ways. So for that first one, we have a certain amount of heat added to 1 mole of a gas in a sealed container. We could use the data to think about how the temperature changes when the heat was added to think and determine what the heat capacity was. That's what we see right here with the students' work. So we could work through to figure out what the heat capacity is in increments of R and find that it's really close to 5/2 R. So we think about 3 translations that would be present and another contribution of R that would get us to a total of 5/2. That's applicable for a linear molecule. What type of linear molecule? N2 would be an example. Many examples, right, of linear molecules that this would apply for. And again, because it's at constant volume, we're not adding in another increment of R. So the point of this question was to use the data to determine how many increments of R that we would have, and then connect that to a plausible molecule. As I look at the students' work, makes me think as a teacher, I need to more frequently include units when discussing a question like this in the class. This worked without omitting units throughout, but I found because heat capacity can be expressed in different ways, per mole, per gram, there were other parts of the exam where lacking that information, some students went astray. So I'm just pointing out it works within here as we were thinking about this, but I mean R after all does have units. R is 8.314 joules per mole K, and I found by carrying through those, it helped on other parts of the exam. For the second one right here, we have an exothermic reaction, and it asks, does the enthalpy change increase, decrease, or remain unchanged at a higher temperature? When I say we have the ability to answer this and not provide a general overview, some folks tried this and didn't really know where to get at it. They would discuss in general terms what enthalpy was, but when I say we have the ability to answer this, we had a discussion where we're looking as the temperature change, does the enthalpy change? Because we're, again, not looking at enthalpy in an absolute way. We're looking at the difference between products and reactants when we're thinking about the enthalpy change for a reaction. So some folks would then add an image like this, reproduce this sketch and suggest that it would change. But an even better response would be to consider, do the slopes themselves change or not? And again, that's something we have the ability to answer as we think of Kirchhoff's law. The difference in the slope is dependent on whether there is a difference in the heat capacity when we compare the products and the reactants. And the heat capacity, that comes back to the contributions to the heat capacity based on the particle motion. So we have in our balanced equation, they're all ones. We have a nonlinear molecule and a linear molecule. And in the products, we have a linear molecule and a nonlinear molecule. So if we were to add up the contributions to the translations and the rotations within our comparing products and reactants, they're the same. There is no change in the heat capacity. So that tells me the lines here would have the same slope. They'd be parallel to each other. So the enthalpy change there would remain unchanged. It would have 2 parallel lines. Looking at structures of solids, first one was considering lattice and motif. Folks did a nice job bringing in a lot of different features here. I think this one's a little bit tough to explain in words sometimes, but I was seeing some nice discussion about different crystal lattices that could tessellate and fill up the 3-dimensional space. How with the crystal lattices that we're filling up, there were different lattice points that we would associate a motif with. How that motif might be a single atom, let's say within a metal. How we would have multiple atoms within our motif, like with an ionic compound. And there were even some nice responses showing how with something like here with graphene, we could have 2 atoms associated with a lattice point that would be off of that. And once we constructed the entire ensemble of motif and crystal lattice, that's where we had the image of the crystal structure emerge. For the second one, it began by doing some bookkeeping, taking the picture right here, and determining what the empirical formula is. So this is definitely an important skill that we want to have. So as I look at this, I see 4 cations, the dark spheres entirely within the unit cell. For the anions, I see 8 at the corners, all with a contribution of 1/8, and then 1 of them in the center. So that leads to my empirical formula, my formula of 4:2, or an empirical formula here of 2:1 for the cation to the anion. If I were to look at the cation, the coordination number, that would be the immediate neighbors. For this cation, I see 2 different anions immediately adjacent to it. I could visualize that for each of those. And given the empirical formula, that means the coordination of the anion has to be 4. If I look at the one right in the center, okay, that's also consistent, as it has 4 cations immediately adjacent to it. And when I say it has to be, remember we saw a connection between the coordination number and the charges that they would have consistent with the empirical formula. So these would be the coordination numbers I would be working from. Thinking about then for the ionic radius, there was some general discussion about how the cations were oftentimes smaller in general, but what does smaller mean compared to an anion? My thought within this was the coordination number that you could have for the cation. The smallest possible coordination number as we think about a 3-dimensional structure is 2. Okay? It's going to have, as we have our 3-dimensional space, it's going to have at the very minimum anion neighbors on each side. So the very smallest coordination number we'd have would be 2. What dictates the coordination number? That was determined by the relative size of the cation to the anion. Several folks had nice images sort of discussing what that meant, reproducing this image like you see on the left. And sort of my train of thought is if the coordination number is only 2, that's the absolute minimum we have, which means that the size of the cation relative to the anion is very, very small. So that would be my sort of overall analysis here. It built on first seeing what the coordination number was and then interpreting the small coordination number of 2. Looking at this last part, aspects of bond enthalpy. This first one involves calculations involving mean bond enthalpy data and standard enthalpy of formation data. Here's some students' work on it. So these were very well done, where I see initially a balanced combustion reaction, which is great. Looking at the standard enthalpy of formation data, we see that that was provided information. There's provided information in the table for everything except for the O2, but as this student noted, it's an element in its standard state, so we wouldn't have that have a value. It has a value of 0. And we see the students come to the same answer for these exothermic reactions. If we look within the second one right here, I'm seeing some nice features of Lewis structures being drawn to make clear within one's analysis what bonds need to be broken or formed. The math then that accompanies it, this student on the left was doing it summing up bonds broken minus formed. The student on the right here was using an approach that personally I would be using of thinking about how breaking bond is endothermic, forming bonds is exothermic, and then we put together those 2 terms. So really nice work in both cases. As far as which of these is a more accurate value, there's a difference of opinions here. So the student on the left is favoring the standard enthalpy of formation, and the one on the right thinks that the bond enthalpy would be more accurate than the standard enthalpy of formation. I'm going to come down and agree with the student here on the left, because when we're thinking about mean bond enthalpy values, these are representative values for a lot of different molecules. I wouldn't go as far as say they're simply averages from every molecule to ever exist. I would say they are representative of different molecules that have carbon-hydrogen bonds, carbon-carbon bonds. And so with the standard enthalpy of formation, it's talking about these specific molecules, whereas the bond enthalpy values is taking the parts, and there'll be more variability because it's looking at them in a general way. that last part, looking at the influence of various factors on the strengths of bonds in a molecule. First thing I was looking for was, did the student use provided data to construct an argument? So instead of talking in general terms, I was looking for the use of the provided data and constructing an argument with that. In class, I discussed 3 factors: bond order, size, and the influence of lone pairs. But I also pointed out that you got to be careful with the comparisons that you make, because there can be competing factors in play. Students at times brought in electronegativity. I sort of find this is a tougher case to make. Okay, you could look to see carbon with these different halogens and conclude that fluorine's the most electronegative. But then if we were to just look right above it and consider carbon with oxygen, carbon with nitrogen, we end up with contradictions that are not consistent with that. Oftentimes, electronegativity, what we might be looking at are actually aspects of size. Because if we're looking at fluorine, chlorine, bromine, fluorine's the smallest within here. So in some ways, that's best explained in terms of a size factor rather than electronegativity. Other folks brought in, what did it mean to be bonded to hydrogen? As I look at this, I do see bonds to hydrogen being quite high, but I come back to that. Seems like that's once again consistent with aspects of size. If hydrogen's the smallest, quite small that we would have, then the bonds would be having greater bond enthalpy values for that particular reason. But once again, this one I was looking for using the provided data, and there's not necessarily a real simple statement that one size fits all across all of these. So there was a lot for me to digest.